Okay, so today we have a special Origins seminar, and with us we have Rory Bowens, who is a graduate student working at the University of Michigan with Michael Meyer, and he did his undergraduate work at Penn State University. So whenever you're ready, take it away.
Thank you. Let me share the screen. All right, I think that's all good. And since a lot of our listeners are online, I'll use the mouse to gesture to things so that everyone can see it. So hello, everyone. My name's Rory Bowens. I'm presenting MIRAC-5 and METIS, near and long-term prospects for ground-based mid-IR astronomy. So in this talk, I will begin with some background on why mid-IR direct imaging, and specifically why from the ground, before moving into MIRAC-5 and the GeoSnap detector and some of the science prospects for it. After that, I'll look a bit more at the long-term plans for mid-infrared astronomy with METIS on the ELT and its science prospects. And finally, I will conclude. So let's begin with some background on why mid-IR direct imaging. I'd like to start with this statement that the mid-IR observations can touch all areas of astronomy. And so this can include just a large variety of targets, mainly because the mid-IR can probe a wide temperature range and through dust, which allows it to see phenomena that are not normally visible. And so this gives you access to this rich spectral diagnostics that you would not be able to obtain with other wavelengths alone. So some examples include you can observe protoplanetary disk. And when you look at those, you can obtain information that can complement existing ALMA data by looking at the warmer molecular gases in mid-IR. You can also look at exoplanets. And so through direct imaging in the mid-IR, you can obtain information on the orbital parameters, their internal structures, their atmospheres, weather, seasons, on and on. There's also work that can be done in the solar system. So with mid-IR imaging, you could look at the D to H isotope ratios coming off of cometary volatiles. You could also use this to observe the atmosphere of Mars, which has, with its scale height, would be appropriately fit for a ground-based mid-IR mission. And you can also push mid-IR to more extreme areas. For example, you can look at the regions around supermassive black holes. So while we know that the black hole mass and the spheroid mass are connected, there's still some questions about why this correlation exists. And so with the mid-IR, you could observe the regions that are normally hampered by the dust, and you would be able to attain better understanding of the geometry and dynamics of said regions. And those are just a few examples. There's other possibilities such as high redshift galaxies, which would be redshifted into the mid-IR, low mass brown dwarfs, evolved stars, gamma ray bursts. The list of possibilities for the mid-infrared is quite extensive. But one thing that I didn't mention during that prior slide is all of those science possibilities are things that are planned either for near-term or long-term ground-based systems. And so I'm sure a lot of people are wondering, why do this work from the ground? Why not do a James Webb Space Telescope, which should surely be superior for these sort of observations? And it is true that James Webb Space Telescope is incredible and really good for a lot of mid-infrared work. But there are regimes where these ground-based systems are necessary, and that mainly comes from when you need to have fine spatial resolutions, which can only be obtained if you have very large sized primaries. So even current ground-based systems are going to have 6.5 meters or greater. And eventually, if ELTs, you'll be able to push up to the 30-meter regime. And it also is important for when you need high contrast. So here I show raw contrast from near on VLT with its annular groove phase mass coronagraph. And in comparison, I have a data point from Rigby et al. 2022, MIRI's raw contrast. And what you'll notice is that although we don't quite even have a curve yet for MIRI, and this will hopefully improve with time as they continue to better understand the system, we can already see that current ground-based systems are definitely going to be competitive with James Webb Space Telescope when you're in these contrast-limited regimes around bright stars, so less than 7th magnitude. And therefore, if we put resources into these ground-based systems, we'll be able to reduce the subscription numbers for James Webb. We'll be able to hit areas that only the ground-based systems might be able to hit. And for areas where they share data, we'll be able to compare the performance of the instruments and help to calibrate them. So there's a lot of advantage to supporting James Webb Space Telescope with these ground-based mid-IR missions. And homing in on my area a little, I'm focused mostly on ground-based imaging for studying planet formation models. And so, as I mentioned, with direct imaging, you can obtain planet luminosities, temperatures, atmospheric compositions. And I'm sure all of you are familiar with this one plot that everyone that does planet work has seen, the plot of discovered planet mass versus orbital period, and the ever persistent goal of pushing this data down towards the Earth-like regime. And so through this direct imaging, we can obtain more data in these areas that have a limited amount of observed targets. And that will help us to constrain formation models, which are critical to our understanding of most planets, as usually we only have a few data points to work with. So for example, this could be used to resolve questions related to the formation location of planets. Do they form closer in, or do they form further out in their disk and migrate inwards, which I will come back to later on. So if you'd like to know more about these open questions, I would refer to Gowdy, Christensen, and Meyer 2021. So we understand that there's a lot of value in these mid-infrared direct imaging campaigns. Let's talk about the near term with MIRAC and the GeoSnap detector. So MIRAC-5 is this evolving sequence of ground-based mid-IR cameras. It started with the original MIRAC in 1988, which was actually a collaboration here in the University of Arizona with Smithsonian Astrophysical Observatory and the Naval Research Lab. And over the years, MIRAC has continued to evolve and experience new designs and new improvements. With the current one, MIRAC-5, I show here on the left-hand side. So MIRAC-5 is mated to another system, Blink, which we use for re-imaging the optics, or re-imaging the light from the MMT into MIRAC-5. And the main improvement that MIRAC-5 has over its predecessors, we've added this new GeoSnap detector. So GeoSnap is a 1024 by 1024 mercury cadmium telluride array that was developed thanks to work by University of Rochester and Teledyne. And the main benefit of GeoSnap is that it has this very deep well, fast readout, and low noise. So our GeoSnap has a quantum efficiency of about 65% in the 3 to 13 micron regime, a well def of 1.2 million, and then a frame rate of about 85 hertz. The baseline GeoSnaps that Teledyne produces are slightly different from this, with the main changes being, with an anti-reflection coating added, you can improve that quantum efficiency to about 90%. And the baseline GeoSnaps are actually full 4-quadrant devices, so they're 2048 by 2048. But even still, this detector that we have will be incredible for MIRAC. If you're doing ground-based mid-IR astronomy, the biggest issue you run into, besides turbulence in the atmosphere, which you can fight via adaptive optics, is that the atmosphere is emitting in the mid-infrared. And so you really need these deep wells and fast readouts, otherwise you'll saturate well before you'll get any reasonable signal from your source. And so the GeoSnap was pushed up to, from originally a 5-micron device up to 13 microns, thanks to work by University of Rochester. And they were able to significantly reduce noise that was caused by tunneling in the GeoSnap. And so we did some tests in our lab for the noise properties just to make sure GeoSnap would be sufficient. And we found that for a fairly typical 85 hertz read with a half-well observation, that we achieved a shot noise that significantly dominated over our read noise and our dark current. And if you want the specific values, I have a paper from SPIE that covers this in more detail. We also found the GeoSnap does not have excess low frequency noise. So this was a problem which impacted a previous detector, Aquarius, and others as well. So that helps to really improve what you can do with it. But GeoSnap does suffer from something called 1/f noise. And so we've not been able to rule out the origin of this. We have determined it's not caused by the mercury cadmium telluride. But we did noise test on this as well and found if we spatially modulate the signal of the source, so basically we have a mirror that's going to chop the signal back and forth between two locations. And apologies to online, I was starting to do hand gestures and realize no one can see those. But basically we chop back and forth between two locations. And if we do this at a frame rate of about 0.1 hertz, you can significantly reduce the impact from the 1/f noise without increasing the noise due to these multiple readouts. And so it's not negligible. It ends up being for an 80% well deaf, you get about a fifth the noise is the 1/f compared to the shot noise. So not negligible, but we're working on pushing as low as we can so that it won't significantly impact the observations. And so just a little bit more on the design of MIRAC-5 before getting into the science. Here you can see a ray diagram of MIRAC-5. It was designed for MMT and Magellan, although right now it'll only be planned for the MMT. So the rays enter at the f/15 focal plane into this blink. And then in blink, you can see the chopper, which will help to spatially modulate it, passes through an aperture wheel, bounces around more through the filter wheels, and finally lands on a GeoSnap. And so given the 1024 pixel format and the 18 micron pixel pitch, this ends up achieving a 19 arcsecond field of view at the MMT. And we end up oversampling the diffraction limit at 10 microns by about 10 times. So it'll be perfect for our observations. Here are just a few more images. You can see one of the filter wheels for MIRAC-5. There are two that can be used in conjunction. There's also a pupil wheel, variable cold stops, and here you can see the chopper. So the chopper has a 1 degree beam angle, which ends up throwing the source about half the field of view on the sky. And the transition time for the chopper we've estimated is about 5%, so it won't significantly impact our efficiency. And we also, over the summer, I tested an accelerometer that we've attached to the chopper. So previously, when you were on the mountain, you had to manually control an excess torque due to gravity as you tilted the detector plane. But now with this accelerometer, that should be handled automatically. So you no longer need to assign some poor grad student to manually control that. And MIRAC-5 will be taking advantage of the new MAPS-AO system. So I'm sure everyone here is a lot more familiar with MAPS than some of my usual audiences. It's the MMT Adaptive Optics Exoplanet Characterization System. So this is a 336 actuator adaptive secondary mirror, which has two pyramid wavefront sensors, one which operates in the visible and one in the infrared. And these work on a 1 kilohertz adaptive optics control loop. So here you can see an image of the 336 actuator mirror, as well as an image of the visible pyramid wavefront sensor with the modulation enabled. So MAPS actually, I think, has just finished up its first commissioning run in the past few days. And in the future, there will be a few more commissioning runs, and we hope that it'll be ready to be used sometime in 2023. So let's talk a little bit about the science that we'll be able to do with MIRAC-5. So MIRAC-5 will be background limited around 13th magnitude. And when you're in the contrast limit, it should be competitive to James Webb Space Telescope, as long as the primary has a magnitude of 7 or less. And so with MIRAC-5, you should be able to study objects in protoplanetary disks, study young brown dwarfs to determine if they have their own disk around them, and also observe known gas giants. And so I'm planning a science run of MIRAC-5 already to observe several gas giants which have been discovered in near IR, even before we have a coronagraph installed on MIRAC-5. So these are wider orbit targets that are therefore accessible even before we upgrade with a coronagraph. And that includes Kappa Andromeda B, shown here, HR 8799C, shown here, and the final target, GJ504b, shown here. So as I mentioned, all three of these targets have been observed in near IR, and by observing them in the mid-IR, we'll be able to obtain more photometric data to better constrain their models. And actually, for GJ504b, it has a cool temperature of around 550 Kelvin, and we've estimated that we should be able to obtain a photometric detection of ammonia around that target. And so these estimates began with the Apollo atmospheric codes. We generated spectra for GJ504b with and without ammonia present. And the goal of this was we wanted to not only determine could we find ammonia, but if we could, what would be a filter that would achieve the highest signal to noise ratio for that detection. So we used Apollo, and we identified that these two valleys shown in this spectra here are indeed caused by the ammonia. And we then tried to use a Python code in order to optimize where should this ammonia filter, which here I call the optimal filter, be positioned such that given the existing N prime filter, we could achieve this high signal to noise ratio.
What is Apollo?
What was that?
What is Apollo?
Apollo is an atmospheric code that was being developed actually at Michigan by a postdoc, Arthur Adams, who is now moved on from Michigan. But there's a current paper on it, and there's more improvements being made to the code. So I can share a link to that at the end. But we then use the Helios and Petit models to actually generate these spectra, such as this one shown here. And what we did was we varied parameters such as the planet's assumed temperature, assumed surface gravity, assumed metallicity, and then we also used two different models. And all of this was done to, we would catalog what's the best location for the filter. And we did this for the various inputs in order to try and come up what's the most robust filter that we could purchase such that it will achieve a high signal to noise ratio, even if the parameters are slightly different from what we anticipate. And so we found a filter from about 10.3 to 10.9 microns was able to achieve a high signal to noise ratio. We found that for the assumed temperature of 550 Kelvin, which is the best estimate for GJ, you would get a signal to noise ratio of 3 for this ammonia with about 8 hours of total observation time. And so that was mainly driven by the assumed temperatures, which we went from 300 to 600 Kelvin. So having now stated that we can observe ammonia, I'm sure you may be asking, well, why are we observing ammonia? And that's because the significant abundance of ammonia and therefore nitrogen may imply movement for these companions. As I promised, we've now come back to that comment on formation of planets. So Bosman et al. In 2019 studied the fact that Jupiter has nearly 4 times solar abundance in nitrogen. And they thought that, or they studied and simulated that if Jupiter were to form beyond the nitrogen 2 ice line at 30 AU via pebble accretion, that could achieve the nitrogen abundance that it has, and then it would have to migrate all the way inwards to 5.2 AU for its current location. Now, if you were to look back at the picture for GJ504b, it's only a little bit in from where its ice line is. So this would not be proving with a single observation that, oh yes, all gas giants form much further out and migrate inwards. But if we do find a significant amount of ammonia for GJ504b, this could help to inform future studies for the best approach for this. And then we could start to try and find more statistics on gas giants that have ammonia versus, or gas giants with excess abundance of ammonia. Could this imply that a large number of these gas giants are migrating inwards from this 30 or 40 AU ice line, depending on the system? So I have to still refine a little bit with my predictions, because right now I'm certain that we will be able to determine these if there's ammonia present, but I am still working out to what significance we'll understand the abundance of such an ammonia presence. So that'll be done with Apollo. And I anticipate that if we match the models, that'll be great. It'll show that the models are predicting this well. If we have a disagreement with the models, that may imply that something went amiss with my calculations, that maybe there's something wrong with the models for this prediction, or maybe GJ504b is some unique case and we'll need to observe more targets firsthand. But regardless, this will be a great first step in understanding the nitrogen abundances for some of these targets. So in the future, MIRAC-5 will be upgraded with a coronagraph, and that will be an annular groove phase mask, which can be supportive of a Quasit control loop. And with that, we'll be able to observe a lot more targets than just some of these wider orbit near IR targets. So first of all, there will be some closer in near IR targets, EPS Indy AB or 51 ARI B. And so with a coronagraph, we'll be able to obtain this mid-IR continuums for these targets and complement existing data. There also will be planets that are being discovered thanks to archival radial velocity data. And those are targets that would only be visible with mid-IR observations. And so if we get a coronagraph and are able to observe those, it will be a great pool of new data. And then you'll be able to observe a wide variety of forming protoplanets as well. And so there's a lot of possibilities for MIRAC-5 in the future. Right now, the plan is once MAPS has been commissioned, which will hopefully be all wrapped up within the first few months of 2023, we will be able to install MIRAC-5 at the MMT later that year. And so that, I'd like to transition now a little bit more into the long term, talking about how mid-infrared astronomy will change as ELTs come online. So for example, Arizona will actually be home to one of the first ELTs with the LBTI, which can achieve an effective angular resolution equivalent to a 22 meter. And so with ELTs like LBTI, you'll start to push into these much finer resolution spaces that are not achievable yet from the ground or achievable with James Webb. And so I focused on the ELT and the device METIS. So here you can see an example of the ELT. It's in concept art. Hopefully it'll look like that within the next few years. And if you squint, you can kind of see the picture of the car for scale of just how large this thing is. Huh, strange. I just noticed that the mouse on my screen is not lined up with the mouse up there. Whatever. I'll just shift slightly to the left on my screen so that it's better positioned. And here's an image of METIS. And here's an image that I can now guarantee you've all seen before because I managed to put in my presentation twice. As always, our goal is to push into this, I gotta look over here, push into this Earth-like regime. And so with ELTs, this should be much more achievable. I did, what I wanted to do was focus on METIS, which is this mid-infrared ELT imager and spectrograph. And METIS can be used to study several of the targets that I mentioned during the introduction, such as the protoplanetary disk or the regions around black holes. And one of the focuses that I was looking into was this previous estimate by Quans et al. About what would be the exoplanet yield if you looked at just the very nearest stars with METIS and studied the yield via Monte Carlo simulations. So I wanted to repeat this process, but now with more advanced methods. So we no longer would assume that our system was background limited at 2 lambda over d, which is a very optimistic assumption. Instead, we used the latest METIS performance estimates in order to understand where background limits occurred. And I also used new Kepler occurrence rates to try and understand the likelihood of planets spawning at certain locations. And so the goal of my research with this was to understand if we did this survey of just the nearest stars of METIS across 3 bands, the L, the M, and the N2. Excuse me. what would be the yield in exoplanets for such a survey, and in particular, which stars and which bands would be the best to look at. And just a moment, I'm going to take a drink. And so you could effectively divide my project into these three ingredients that you would need to understand the system. The first are the sensitivity estimates from METIS. So we have these contrast curves. I show an example here of 3 of them. And these were done with single conjugate adaptive optics errors, as well as the SCAO errors plus non-common path errors. So you can think of the 2 scenarios as kind of an optimistic versus pessimistic case, with the most likely result from METIS in the future sitting somewhere in between the 2. And so here you can see the L, M, and N2 bands. And what you'll notice is that the N2 band is hitting background limit around 5 lambda over D. Oh my gosh, I keep looking at the computer and so 5 lambda over D, and the other is M around 15 lambda over D, L around 25 lambda over D. So it is important that we don't just make this assumption about the 2 lambda over D, because when it comes to these contrast limited observations, if you do a 1-hour exposure like these curves were done for, if you were to increase that time, when you're background limited, the curves will be able to push deeper, and therefore you could observe planets that may not be quite visible beforehand. But in this contrast limited regime, a longer exposure will not improve your contrast. And so, since a majority of our observation space will be in this contrast limited regime, that will impact the achievability for certain targets. So our second ingredient, effectively, in our study were planet occurrence rates. I worked from the NASA ExoPag Sag 13 report. So in this report, planet radius versus orbital period was divided into bins, with each bin having an estimated occurrence rate for a planet there. And what I did in my Monte Carlo simulations was I would randomly organize the bins, and I would draw from a Poisson distribution to see if a planet would spawn in that bin. And if I got a planet, I would give it a radius and an orbital period from a uniform range from in there. And then if that star already had a planet spawned around it, I would do a mutual Hill radii test just to see if adding this new planet would be stable to first order. And so if it was not stable, I would toss that planet out and continue through the rest of the table. And this could generate a series, this would generate a system around my star. And I would just repeat this process per star and per run in order to generate these planetary systems. With one of the key points being, I assumed all the planets were in radiative equilibrium with their star. And so the final ingredient were the actual stars in the nearby solar neighborhood. I selected stars that were K5 and earlier within 6.5 parsecs. And this was mainly driven by what would be the required integration times for these targets, given their distance and brightness. A declination range was set based on the location of the ELT, and I recovered 18 candidate stars for the survey. And so here you can see an example of all 3 of these features overlaid on top of each other. So the planet occurrence rates from Kepler are given in the background in radius versus orbital period space. And what I've done is for the N2 SCAO curves, I've converted them into this space for each star system. So alpha Cen A is shown here, alpha Cen B, and I show the top 5 candidates plus number 6 Tau Ceti. And the main reason I'm only showing these top few is that in a realistic survey, if we were doing this blind approach to try and find targets, we would not be able to allocate that much ELT time to study 18 stars in 3 bands at least. And so I limited to the top 5 because, as you can see, as soon as you're hitting Tau Ceti at number 6, you've already lost a significant number of these best occurrence rate bins, such as the 10% here or 6% here. And so all of these results were then given. I'll go through and describe I'll describe SCAO case, and they're all given for just the top 5 stars. I also present on the slides the with non-common path results as well. So as you can see, we end up with the highest chance of detecting planets actually in the N2 band, with about 71% chance we'll recover at least one planet with this blind survey. And the yield would be about 1.14 planets in N2. And here in these heat maps, I show the actual location we would anticipate such a planet being recovered. So in the N2, our best chance, we would find a planet most likely around 3 Earth radii and 300 Kelvin. For the M band and the L band, it's a similar radii, a bit of a spread. And as you would imagine, the most likely temperature regime rises as you go to M and then to L. Now, what we ended up finding was that the N2 band was superior to the L and M band, with the most yield coming from N2. And we actually found there was about a 42% chance that a planet observed in one of these bands would be visible in at least one of the other bands. And so that's excellent if we want to do multi-wavelength characterization. As I mentioned with MIRAC-5, it's excellent when we have the near IR and mid IR together. And with METIS, we would be able to obtain some of this data in L, M, and possibly N2 as well. Now, I didn't just look at I didn't just look at the very close planets. I also considered what we would be able to obtain from this survey if we looked at the wider orbit gas giants. So this is more comparable to work that we can currently do with MIRAC-5. And to do this, I just used occurrence rates for the gas giants coupled with the assumed stellar ages, which coupled with estimated stellar ages, which I assumed the planets would have similar ages. And I used the Beck's models to then estimate what would be luminosities for these gas giants at wide orbits. With the point being that we no longer were assuming that these are in a radiative equilibrium with their host star. These could have their own internal temperatures, which would thus make them visible at larger distances. Now, there was an issue of our top 5 stars, 4 of them are in binary systems, just by chance. And so if you mark out regions that are considered unstable based on the nearby binaries, you end up with these really small sandwich zones of, I keep doing that with the mouse, sandwich zones of where the background giants could be spawned compared to what we already studied with Sag-13 and what is not going to be stable beyond there. And so we found about a 25% chance that from these 5 targets, you would recover just one gas giant during this blind survey. A majority of that comes from Altair, who's the only target that does not have most of its background giant zone ruled out by binaries. But we also estimated for current known Jovians like Epsilon Eridani or Epsilon Indiae, you could achieve a significant exposure for them with only about a few minutes of observation time. So the power of these ELTs would be immense. And as a final bit of work I did with this METIS estimate, I looked into if we were to observe a target at multiple epochs, how would the yield increase? And so the idea was our Monte Carlo code was actually already taking into account the locations for our planets in terms of where they're spawning and their orbital parameters. And I simply had the code run them for a few more months to understand where the planets would be a bit later, and then estimate what would be the increase in yield for those targets if you looked again a few months later. You can see if Alpha Centauri, when you first look, you recover about 32% of the planets that were 32% of the planets that were spawned for that target. But by looking 3 more times, you can end up achieving about 39% of the planets that were spawned. That may not seem like too much at first, only a few percent, but what ends up happening is if you compare the yield per observation, including repeats, across stars, you find that it's actually worth looking at targets like Alpha Centauri 4 times over before it's ever worth looking at our number 6 target, Tau Ceti, or targets further down. And so in terms of a blind survey, it's really important to do this sort of optimization if you are not sure what sort of targets you'll be finding. And a
Did
question?
you just assume based on circular orbits for the planets, or?
No. So for some of the systems, we estimated inclinations, and this was done based off comparisons of the V sin i's versus other estimates, such as the radial velocities for the stellar, like the star spots. And
So
so
you're assuming that the orbit would be aligned like
with
perpendicular to
the
star?
star's angular momentum. And so I have a paper on this that has the details, but I think for Alpha Cent A and B and Altair, we were able to obtain inclinations, maybe Procyon's if Altair. And then for the other two, we did a D projection, just assuming it could be anywhere in 3D space. And therefore, when we did the Monte Carlo simulations, the ones that had known inclinations, we just worked with said known inclinations each time. The ones with unknown inclinations, that was a part of the Monte Carlos we would pull from whatever projection it landed at. But great question. That was a lot of fun and a lot of pain as I sat there, like trying to understand how these things in 3D would project into 2D and how to work through all of that. It was painful.
Even for the ones with a known inclination on the star, there can still be spin orbit misalignment,
Yeah, and
especially if there's a stellar binary.
and so that's actually, I'll mention a little more in the moment, but so with this, you could push yield from about 1.1 planets to about 1.5 in the N2. But as alluded to, there's some caveats to this work. So actually, some of the main issues that we were worried about were just the evolving Kepler occurrence rates and the future evolution of the contrast curve from METIS. But there were some other things that we wanted to consider. The binaries have an impact on our stability, and that's not just for the wide orbit gas giants. So there's papers that found there can be decreased occurrence rates if you have a binary, that there can be reduced stability for multi-planet systems, and that there's also the fact that the progenitors in the Sirius and Procyon systems would have been closer than their current white dwarfs. And so we did try to estimate the impact for this result and found that if you were to imply this or impose a max of only one planet in a binary system could be stable, you end up reducing our chance of finding a planet in N2 from about 70% to 50%. So it is a loss, and it's fairly large of a loss in terms of chance of success, but it's not detrimental to the program. And then, as alluded to, we had fairly simple models for our planets. They were black bodies. We assumed instantaneous separations. Included in the etc. was indeed the inclinations and how we estimated them, as well as eccentricities, which are less of an important factor for these targets. But so there are certainly improvements that can be made in this work. And I think right now, the main thing that we would like to wait and see more on is how the planet occurrence rates and the METIS contrast curves will continue to improve. Because just swinging back to this picture, you can see that if, for example, this 24% in is real, if these curves were able to push into that, that would be a huge increase in our yield for a survey. But it's also possible maybe these bins are overestimating how many planets there will be. So that's something just to wait for the future as more studies come out. So wrapping things up, there's a lot of advances for the mid-infrared on the horizon. In the near term, we have GeoSnap and MIRAC-5 on the MAPS AO system. And so with that, you should be able to image gas giants and upwards. And there's actually already several promising candidates selected. Some of them I'm planning to observe. Some of them I hope others will be planning to observe. And at least for one of mine, it's possible we may be able to observe ammonia. So an SBIE paper on this is actually available in the archive. And then in the long term, there will be ELTs such as LBTI or the ELT. And so I looked a little bit into METIS on the ELT, which should be able to image super Earths and up. And I found that with METIS, you should be able to obtain a high yield of about 1.5 planets in the N2 through a blind survey. And a paper on that is also available in the archive. So thank you all for listening to this talk. And if you have any questions, please let me know.
So questions in the room or online?
Yeah.
Oh,
I have a question. So how much like contrast do you have left in the contrast budgets for that planet yield? Like how much worse can the contrast be for the yield to like just collapse?
I would say it's complicated because I think that these curves, I really don't have an intuition of if these curves would go up or down as it goes, but even if they went up a bit, near this right-hand side, we're actually getting right near the background limit. So this is a period of around 640 days or so. And so even if these went up, in the background limit, you can expose for longer and push the curves deeper. And therefore, even if you're not getting as many targets at like 100 days, you may still be able to make up for that by achieving more targets at further distances. And of course, this was all for this blind survey. It may be possible by the time METIS is operational, we have a much better idea of what are some targets around these stars. And if you know where the target is, you could probably push your observations to the limits in terms of efficiency.
Yeah, because the last SPIE meeting showed that METIS is probably going to perform worse than all the simulations up to now because of the
water vapor.
The water vapor.
Yeah, that was something I had heard about as well. So I would anticipate at the very least, it will probably rise a bit. And then it may be a question of, can you push it down further once your background limited? And meanwhile, in the contrast limit, it may be that you are not achieving some of these targets, but you'll still be able to achieve targets that are a bit more massive than this.
So how stable is the GeoSnap array, and could you use it for transits, for example? I mean, that's a way to get thermal balance on the planets. If you can get 100 parts per million or something like that.
I would have to get back to you on the stability of GeoSnap. Off the top of my head, I'm not as familiar with it, so I don't want to say something that I'm not certain about.
So I was trying to think of Discovery Space. The ammonia, Mary has a filter centered on ammonia, and with the 4-quadrant phase mask, it ought to be maybe even more than competitive with the observation you're planning to take.
Right. I did do some estimates for MIRI, and I think it should be able to achieve these observations just as well, perhaps even better. And then the argument there, originally the argument would have been if COVID hadn't hit, MIRAC-5 would have hopefully been up a year ago, and therefore it'd be just getting to that data immediately. But even with James Webb, one, I don't think there's any plans for observing GJ504b yet. But two, since this is the sort of work that can be done from the ground, it just makes a lot more sense to do it from the ground rather than trying to achieve JWST time for it. And actually, if there were multiple observations of it, it would be nice to see the results between MIRI and between MIRAC-5 as well.
Anyway, I was looking for another class of observation that you could use as foreign transit. It seemed like something to be worth exploring, but I don't think anybody has, that I know of, has measured the stability of these detectors at the necessary level.
I'll ask into it because you might be right. I've not heard anyone mention stability when it comes to GeoSnap, and that might be something worth looking into.
Any other questions online?
And I realized one final time I looked at this instead of like over here.
So maybe you could invest the stability and investigate the stability when you have your commissioning runs.
Okay, I will add that to the list because it'll be a good question of if no one's done it, we should know it.
When is commission around?
Sometime in 2023. So it's mainly going to depend on how MAPS continues from here because we'll need MAPS to do this. So the hope would be maybe in like April of 2023, but we'll have to see. I would hope.
So for this potential ammonia detection, how extensive was your atmospheric modeling to see whether or not it would actually appear? Like if you expect it to actually appear, did you include things like photochemistry, or was it just purely an equal?
So the models right now were basically, we just went with if this was a very typical target without any sort of more advanced features in our like our Petite or Helios model.
Okay, so
Pretty much, I'm confident that if there is ammonia there, it will be observable. But I am going back now to refine to get a better idea of,
whether it
okay,
should be
yes or no is not the most scientific paper. It'd be nicer to say, we know there's ammonia with X abundance plus or minus some error. As an undergrad, I was told that any scientific value without an error is not useful.
Hey, Rory, I don't know if can you hear me
Yes.
online here? Okay, sorry, my mic wasn't working a bit ago when George was asking his question, so I could probably address that a little bit.
The
And
GeoSnap or
yeah, the stability of GeoSnap, yeah. My concern there would be the pixel level 1/f noise that exists. That's a huge contributor to low noise applications and would be a problem for that type of sensitivity on transits, I think.
No, it doesn't seem to me as a killer problem if you're chopping, as Rory
well the
tried.
I mean with the
Oh,
chop,
that is true.
it was down to 20% shot noise, which I still felt was somewhat significant. I'm not sure what level we need for the transits.
And you can run slower as you know the 1/f noise contributions scale with the frame rate, so that would help too.
other questions? If not, let's thank Rory again. And I'll go ahead and stop the recording.